Coating a fighter jet engine with diamonds might sound like an incredibly lavish fantasy. Yet, in the realm of modern military aviation, this is not a luxury, it is the ultimate physics of survival. Inside the heart of a supersonic jet, temperatures reach levels that can easily melt steel. Protecting the airframe from this thermal hell is the crowning achievement of modern engineering. Even the world's most advanced fifth-generation fighter, America's F-35 Lightning II, has faced severe limitations when dealing with the extreme thermal loads generated during sustained supersonic flight. When pushed to the absolute limit, extreme engine heat can degrade protective coatings. This forces military planners to make painful compromises between raw speed and structural longevity. But South Korea's homegrown fighter, the KF-21 Boramae, has introduced an entirely new paradigm. It aims to conquer this thermodynamic nightmare using a revolutionary nanotech solution. By implementing a nanoscale diamond thin film coating, Korean scientists have unlocked an unprecedented method of heat dissipation, turning a jewelry-grade material into a military shield. This incredible material conducts heat 5 times faster than copper. It allows the KF-21's jet engine to safely manage extreme internal temperatures and dramatically boost flight performance. I am Ethan Walker, and today on Weapon Science, we will dive deep into the physics of the KF-21's diamond cooling and the secrets of the chemical vapor deposition process. To truly appreciate this breakthrough, we must first understand the brutal laws of thermodynamics. Any heat engine's efficiency is fundamentally bound by the famous Carnot cycle. According to these thermodynamic laws, the greater the temperature difference between the engine's heat source and its exhaust, the more mechanical work and thrust the engine can produce. Therefore, to make a fighter jet fly faster, climb quicker, and operate more efficiently, engine designers must push the combustion chamber's temperature as high as humanly possible. But this pursuit of raw power immediately collides with a physical wall, the melting points of the very metals used to construct the engine. Copper, steel, and nickel all have their limits. Inside a modern military turbofan engine, the gas temperature routinely exceeds 1500 degrees Celsius. This is well above the melting point of most conventional superalloys. In essence, a jet engine is constantly operating in an environment hot enough to melt itself. Every second of flight is a delicate dance on the edge of structural self-destruction. For decades, this thermal barrier has acted as a heavy chain around the necks of aerospace engineers. Pushing for more thrust meant risking a catastrophic blade failure mid-flight. Simply blowing cool bypass air over the turbine blades is no longer enough. The sheer intensity of the heat flux demands a physical shield that can block the thermal energy entirely. To solve this, engineers historically turned to ceramic-based thermal barrier coatings, or TBCs. These materials act as excellent insulators, slowing down the transfer of heat into the metal. However, traditional ceramics possess a critical, fatal flaw. Because they are designed to block heat rather than conduct it, they trap thermal energy within their own structure. Over long periods of exposure to extreme temperatures, this trapped heat causes severe thermal expansion mismatch. The ceramic coating begins to crack and flake away from the metal. This flaking, known as spallation, is an engine designer's worst nightmare. Once the coating fails, the underlying metal is instantly exposed to the full 1500-degree blast. The resulting structural failure can destroy the entire turbine stage in a fraction of a second, leading to a catastrophic loss of thrust and the potential crash of the aircraft. This thermodynamic battle is not theoretical. It is a real-world crisis currently affecting the most expensive military project in human history, the American F-35 program. The F-35 is powered by the Pratt & Whitney F-135 engine. While it is incredibly powerful, this single engine configuration must generate massive thrust, resulting in extreme thermal stress. During high-speed operations, the F-135's internal temperatures frequently redline. This causes the ceramic thermal barrier coatings on its turbine blades to wear out much faster than anticipated. This premature coating degradation drastically shortens the engine's operational lifespan. It forces frequent, highly complex maintenance overhauls that drain military budgets. Furthermore, in hot and dusty environments like the Middle East, the intake air is already warm, reducing the engine's natural cooling efficiency even further. When fine sand particles enter the combustor, they melt into a glass-like substance that clogs the tiny cooling holes of the turbine blades, accelerating the coating's decay. To protect the F-135 engine from self-destruction, pilots are often restricted from using full afterburner for extended periods, limiting the F-35's tactical performance. Engineers have tried to make the ceramic coatings thicker to offer better insulation, but this introduces a new physical penalty. Weight. Every extra gram increases centrifugal force. At tens of thousands of RPM, a heavier coating can cause the blade to snap under its own immense G-forces. The F-35's engine was trapped in a cycle of thermal compromises. This is where South Korea's aerospace researchers decided to break the mold. Rather than trying to insulate the heat, they asked, what if we could move the heat away instantly? This counterintuitive concept using high thermal conductivity instead of insulation led them directly to the ultimate thermal material in the universe, diamond. In solid-state physics, diamond is renowned not just for its hardness, but for its unmatched ability to conduct heat. It is a thermodynamic miracle material. Unlike metals, which rely on free electrons to conduct heat, diamond conducts heat through the collective vibration of its tightly bound carbon atoms, a phenomenon called phonons. Because carbon atoms are extremely light and bound by the strongest covalent bonds in nature, these heat vibrations travel through diamond at nearly the speed of sound. This gives diamond a thermal conductivity of over 2,000 watts per meter Kelvin. To put that in perspective, that is 5 times higher than pure copper. Furthermore, diamond has an incredibly high melting point of 3,550 degrees Celsius, making it virtually immune to the temperatures inside a jet engine. If engineers could wrap a turbine blade in a microscopic layer of diamond, they would create an indestructible shield that flattens heat spikes before they can damage the metal. But you cannot simply glue a diamond onto a turbine blade. To achieve this, Korean scientists had to master the art of chemical vapor deposition, or CVD. CVD is a process where a solid material is grown atom by atom from a gas phase. It is a molecular scale magic trick that allows diamonds to be grown directly onto metal. First, the chamber is sealed and evacuated to a near-perfect vacuum. Then, a precise mixture of methane and hydrogen gas is injected into the chamber. Next, powerful microwaves are beamed into the gas. This intense electromagnetic energy tears the gas molecules apart, creating a glowing violet-purple plasma. In this plasma state, methane molecules are stripped of their hydrogen atoms, leaving behind free, highly reactive carbon atoms floating in the chamber. These free carbon atoms descend onto the heated turbine blade. As they land, they begin to bond with each other, slowly forming a continuous diamond crystalline structure. The hydrogen gas plays a crucial role here. It acts as a molecular eraser, etching away any carbon atoms that try to form weak graphite instead of strong diamond. By fine-tuning the ratio of methane and hydrogen and controlling the plasma temperature, engineers can grow a flawless nanocrystalline diamond film just a few micrometers thick. However, this process presented a massive engineering hurdle. Diamond and metal do not naturally like each other. In fact, they have wildly different thermal expansion coefficients. When the engine heats up, the metal turbine blade expands much faster than the diamond coating. Without a solution, the diamond film would simply peel off under the stress. To solve this, South Korea's materials scientists developed a secret weapon, a multi-layered transition buffer zone between the metal and the diamond. This buffer layer is composed of a unique alloy that possesses intermediate thermal expansion properties, acting as a molecular shock absorber between the two materials. This breakthrough represents the pinnacle of modern nanoengineering. It is a secret technology that only a handful of advanced nations possess, and it is the key to the KF-21's success. Once the diamond coating is successfully bonded, the turbine blade is ready to face the absolute worst conditions a jet engine can throw at it. Now, let us look at how this diamond shield behaves in action. In a standard engine, a major issue is the formation of localized hotspots. These hotspots occur because the combustion gases do not flow perfectly evenly. They create concentrated pockets of heat that can soften the metal at specific points. But on the KF-21's diamond-coated blades, hotspots are physically impossible. The moment a pocket of heat hits the blade, the diamond film spreads it out instantly. This rapid heat dispersion ensures that no single part of the blade ever experiences dangerous thermal stress, drastically reducing the risk of material fatigue and cracking. This is similar to how a high-quality copper frying pan distributes heat evenly to prevent food from burning, but executed on a nanometer scale at supersonic speeds. By eliminating hotspots, the KF-21's engine can operate at a much higher average temperature. This translates directly into a massive boost in thrust and fuel efficiency. But the diamond coating does not work alone. It operates in perfect harmony with another advanced aerospace technology, film cooling. Film cooling works by bleeding cool air from the compressor and venting it through tiny holes in the turbine blade, creating a protective boundary layer of cold air. In traditional engines, this cooling air quickly mixes with the hot combustion gases, losing its effectiveness and forcing the engine to use more compressor bleed air. However, when combined with a diamond coating, a powerful synergy occurs. The diamond film absorbs heat from the blade and transfers it directly to the cooling air film. This makes the film cooling process significantly more efficient, allowing the KF-21 to achieve superior cooling while using a fraction of the compressor air. Using less compressor air for cooling means more air can be directed into the combustion chamber, resulting in a direct increase in thrust and a longer operational range. While the F-35 must constantly struggle with thermal limits and high fuel consumption, the KF-21 can maintain high speeds for much longer periods without overheating. This thermodynamic advantage is not just a triumph of physics, it is a massive strategic victory for South Korea on the global stage. Historically, South Korea was forced to rely entirely on foreign nations for advanced jet engine technology, leaving its national defense vulnerable to export controls. But by developing its own cutting-edge material science and manufacturing techniques, South Korea is paving the way for complete technological independence. The mastery of diamond nanocoating technology ensures that South Korea's future fighter jets will be powered by homegrown engines that no foreign power can restrict. This technology has far-reaching implications beyond military aviation. The ability to deposit diamond films on metals is highly sought after in many other industries. In the world of high-power electronics, heat is the ultimate enemy. Diamond-coated heat sinks can allow microprocessors to run at speeds that were once thought impossible. From space exploration to clean energy, the nation that controls the flow of heat will control the future of technology. South Korea has positioned itself at the front of this race. The story of the KF-21's diamond engine is a testament to what can be achieved when scientific imagination is backed by relentless determination. What seemed like an impossible dream growing diamonds on spinning metal blades has become a concrete reality that secures the skies of South Korea. It is a beautiful reminder that sometimes the most elegant solutions to our most complex engineering problems are hidden in the most precious materials of our planet. As the KF-21 Boramae continues to push the boundaries of flight, its diamond heart will ensure it remains a symbol of technological triumph for decades to come. We hope this deep dive into the physics of diamond coatings and jet engine thermodynamics has been as fascinating for you as it was for us to create. What are your thoughts on South Korea's diamond-shielded engine? Do you think this technology will redefine the future of military aviation? Let us know in the comments below. If you enjoyed this episode of Weapon Science, don't forget to subscribe, hit the like button, and turn on notifications so you never miss another deep dive into military tech. Thank you for joining us on this incredible scientific journey. Until next time, keep looking beyond the textbook and stay curious. I'm Ethan Walker, signing off.